Welcome to The Explainer. Today we're going to look at what happens when the nice, clean science you learn in a textbook slams right into the messy, unpredictable, and frankly, kind of mysterious real world. Okay, so let's just dive right in. In school, science feels like it's got all the answers, right? You get a formula, you plug in the numbers, and voila, you get a perfect result. But ask any engineer out in the field, and they'll tell you that's just not how it works. Sometimes a single, tiny detail that nobody thought to account for, a hidden variable, can make the whole system just fall apart. And that actually brings us to our first case. It's a real-world chemical detective story that happened at a city water treatment plant. And it all started during a major supply chain crisis. So this plant needed a chemical called a coagulant, specifically iron sulfate. Its job is pretty simple. You add it to the water, and it makes all the little bits of dirt and gunk clump together so you can filter them out easily. But their normal supply got cut off, so they had to scramble to find a new source. They found a new supplier, and when they looked at the paperwork, the product seemed absolutely perfect. I mean, according to every official spec on the sheet, this new chemical was identical to the old one. Same purity, everything checked out. It should have been a seamless swamp. But it wasn't. The second they started using the new stuff, the whole water purification system just collapsed. The water coming out the other end was even dirtier than the water going in. So what in the world happened? Well, instead of making those nice big clumps that are easy to filter, this new coagulant did the exact opposite. It created this fine, stable cloud of tiny particles that just stayed suspended in the water. This murky mess then flowed down the line and completely gummed up the filters. Total disaster. After a ton of investigation, the chemical engineers finally pinpointed the problem. Get this, it was a ridiculously small, unlisted impurity of titanium oxides in the new batch. We're talking less than 1/10 of 1% of the material. And that's the crazy part. It was a detail so insignificant, it wasn't even required to be on the official spec sheet. But it was powerful enough to sabotage an entire municipal process. It's just a perfect lesson in how these hidden, real-world variables can have massive consequences. But some real-world problems are more than just finding a hidden variable. Some of them point to these huge gaps in our basic scientific understanding, mysteries that we still can't solve. Which brings us to a really well-known industrial hazard that, you won't believe this, is still a total puzzle for modern physics and chemistry. Okay, the setup sounds almost laughably simple. You've got a standard high-pressure oxygen cylinder. Now just imagine a tiny, tiny trace of oil gets on it. Maybe a worker with a greasy rag just brushes against the valve. The result? A massive, violent explosion. And this is where we run into a major scientific head-scratcher. See, according to everything we know about explosions, it's the fuel that explodes. In this case, the fuel is just a few milligrams of oil. That should at most create a tiny little pop. But what you actually get is an explosion with the force of kilograms of TNT. The energy release is just enormous, way more than the oil could ever contain. And pure oxygen isn't supposed to be an explosive. So where is all that energy coming from? This kind of weird, unexplained behavior isn't just for dangerous industrial sites. You can actually find another one of these fascinating scientific mysteries right in your own kitchen. Yeah, I'm talking about that crusty scale that builds up in your kettle. It all comes down to a really basic chemistry concept called solubility. Basically, how well something can dissolve in a liquid. Now, for almost everything you can think of, the rule is super simple. The hotter the liquid, the more stuff you can dissolve in it. It's why you can dump way more sugar into a hot cup of tea than you can into a glass of iced tea, right? That's the rule. But the main chemical that creates that kettle scale, it decides to play by a completely different, totally backward set of rules. It has something called reverse temperature solubility. And here's where it gets really weird. Calcium carbonate, that's the main ingredient in lime scale, it actually becomes less soluble as the water gets hotter. So as you boil your kettle, it comes out of the water and sticks to the heating element. But here's its chemical cousin, magnesium carbonate. It looks almost identical, but it behaves normally. It gets more soluble in hot water, so it doesn't cause any scale. And that's the mystery. Why? Why does one molecule follow the rules while its almost identical twin just completely breaks them? I mean, science has some really complex models and ideas, But there is no simple, clean explanation for this. It's still an open question. So when you hear these stories, the failed coagulant, the oxygen explosions, the weird kettle scale, it might sound like science is failing, but it's actually the exact opposite. They're this incredible reminder that the world is still full of genuine mysteries to solve. These unanswered questions show us that our technology is nowhere near perfect, and there is just so much left for us to figure out. And really, this is an invitation. It's an invitation to every curious student, every engineer, every thinker out there. There's this illusion that science is basically done, that all the big discoveries have already happened. But the opposite is true. These gaps in our knowledge, these real-world puzzles, these are the frontiers. This is where the next huge breakthroughs are going to happen. The only question is, which one is waiting for you? Thanks for watching.